Hey guys, this is a walkthrough for the CLUViz elements of our honours project. Is secure communications possible without a key exchange? So as a part of our project, we've developed a series of images and animations using CLUViz to visually demonstrate how an encryption system based on rotations in 3 dimensions and even 4 dimensions could work in accordance with the double padlock protocol. CLUViz is a software tool for 3D visualisations that interprets a script language called CLUScript, which has been designed to make mathematical calculations and visualizations very intuitive. So this is the CLUViz page on the wiki, and it nicely summarizes the CLUViz work we've done over the course of the project. And as you can see, it goes through 3D and the 4D work and explains how they work and their various features. So to download CLUViz, if you just go to this wiki page, you can download it from either going to the CLUCalc website just here, and that takes you to this website, and it gives you plenty of information and resources in writing your own programs, or you can either go to the direct download link just there. So after you download and install it, which really doesn't take that long, and I think it's only about 32 megabytes, you just click on the link, click on the icon at the bottom, and it will open up like this. And as you can see, once you've opened it, you're given 3 windows: your main editor, which is where you program; your output, which is a great resource and we predominantly used it for testing; and also your visualization page, which does the actual 3D simulations and eventual animations if you so choose. You can also press F1 or click on help up here in the editor tab, and that provides you with a range of resources that really do help you in programming, and it goes through everything, predominantly GA based. So let's exit that. So the first thing we'll do is I'll run through the 3D CLUViz. So we'll load that up. To load up another program, you simply go File, Open, you just choose it. So for us it's the 3D CLUViz Honours. Open it up, and here you go. So I'll just pause that for a second by pulling this down and going pause. Okay, so this is the 3D CLUViz program. I know it looks pretty complicated seeing it for the first time, but I'll run through it and hopefully I'll be able to explain each of the elements to you. Firstly, the dark green sphere in the center with the 3 white unit vectors E1, E2 and E3 that you can see to find the usable space for our rotations. We then have 2 vectors for the rotation axes of Alice and Bob, shown in green and blue that you can see as I spin this around, respectively, which the message vectors are rotated around to provide us with the encrypted message. If you're not sure what that means, please have a read of the wiki, particularly the final report. The next main element of the center diagram is our initial message vector, which you can see in red there, which is the initial message that we're encrypting, and you can change the elements of that vector using the 2 sliders down the bottom, E1 and E2. And even though it's 3-dimensional, the only reason we don't allow E3 to be changed is that's automatically calculated based on your choice of E1 and E2 to limit to a unit length. We then have 3 intermediate message vectors shown in orange and our final message vector shown in purple. And once again, that's just in accordance with the double padlock protocol. The blue and green arcs you see on the screen are between the message vectors represent the direction of the process, with the color representing whether the encryption or decryption is conducted by Alice and Bob, which I'll explain in a sec. Now, in regards to the support diagrams shown on either side, these and these, the two on the left are used to control and display the actual rotation angles of Alice and Bob, and the two on the right show the angle difference between the initial and final message vectors. So you can see the 2 rotation angles over here. We can change them by using the sliders down the bottom, and you can see that changes, and it changes the whole encryption process in the center, and same with Bob. So I'll just leave them there for now. And the 2 on the right over here are probably the most important 2 parts of this animation. As we know that from our 3D analytical proof, that once again you can see from the wiki, the vectors M and M dash, or our initial and final message vectors, can only commute when the 2 rotation axes of Alice and Bob are parallel. Hence, the only time we should see the initial and final message vectors equal is when Alice and Bob's rotation axes are parallel. which naturally, as this shows the difference between M and M dash, and this between Alice and Bob, it means that this should only hit 0 degrees when that hits 0 degrees. Pretty simple. Now I'll turn back on the animation just to give you a brief run through. Actually, before I do that, if we've got, so I'll give you a run through, because with 2D it was a lot easier to visualize, as you can see from the wiki, because you're automatically looking straight down the rotation axes, but it's a bit harder to comprehend in 3D. So if we start with Alice, and say Alice wants to send Bob a message, the encrypted message. Now if we look right down Alice's rotation axes, you can see just over here the initial message vector. Alice rotates it anti-clockwise 185 degrees, as dictated up here, to M1. She then sends that message to Bob. Bob, who then applies his encryption, so we'll look down his rotation axis, so we'll line that straight up, applies a 210 rotation to get from M1 around to M2. So at this point, in regards to the double padlock protocol, this is the equivalent of having both locks on at the same time. Bob then sends it back to Alice to apply her decryption or reverse her rotation. And as you can see, there's a negative 185 degree rotation applied to get from M2 back to M3, which is then sent back to Bob for the exact same thing to reverse his previous rotation to get to M dash. And then, as obviously as I said, as M doesn't currently equal M dash, the rotations do not commute, which is expected, as the two rotation axes aren't in parallel. So I'll turn on the rotation animation now, and as you can see, that animates by having Alice's rotation axis rotate around the sphere on a plane and automatically intercepting Bob, so that every 15 seconds it automatically shows the user that when they're in parallel, that they overlap. So we might see that in a second. Here we go. As you watch this angle come down, just as it hits 0, you'll see this come. So you'll see, there we go. And it's also been implemented so that you can change the speed or pause the rotation. So we can jack that up a lot faster. And in real time, while that's going, we can also change the exact coordinates of the message vector. We can change the rotation angles. And then we can also pause the animation whenever we want. So that's all well and good. So you guys can have a play around with that. Hopefully this has helped you guys visualize what this protocol implemented into a 3D space actually means to some extent. We've also developed a very similar animation for 4D that is about 10 times more complicated, to be honest. And I'll show you that briefly. So I'll just open that up once again. We can just click back over here onto the editor, go File, Open, and we'll just open up the 4D one now. So as you see, these two windows are the same as before, and I'll just move this into the center of the screen. There we go. So this is the 4D. Bear with me for a second. In order to implement the 4D, an additional rotation axis was added for each Alice and Bob. I'll just pause this. For each Alice and Bob, bringing the total number of rotation axes to 4. As you see, there's Alice 1, Alice 2, Bob 1, and Bob 2 now. As a result, 2 support diagrams were added to allow the user to alter the rotation angles of the new rotation axes. As you can see over here, we've now got Alice 1, Alice 2, Bob 1, Bob 2. And naturally there's this corresponding sliders to change those rotation angles, the exact same as with 3D. Also, as with the 3D visualization, we wish to show the vector displacement between each pair of rotation axes during animation to show how it affects the difference in the initial and final message vectors. As a result, 5 more support diagrams were added, as you can see to the right. So every pair of rotation axes, we can see their exact displacement between one another. Now, in order to depict the 4th dimension for the initial and final message vectors, as that's the critical part of trying to implement this into a 4D space, 2 spheres were added as shown in red and magenta. As you can see, the magenta is really small at the moment, so I'll just change something to make it a bit bigger. There we go. The magnitudes of each of these spheres spheres represents the E4 component of each, the initial and final message vector, where obviously the magenta is for the final and the red is for the initial. And they can obviously inverse to correspond to negative numbers. And the vectors of the initial and final message vectors still correspond to the initial E1, E2, and E3 elements. Hence, it was programmed that the initial and final message vectors would only equal when the vectors overlap and the two corresponding spheres were of equal magnitude, which can also be shown by this image here. As in 3D we had this image, we've now got this one as well, that not only shows the displacement represented by these two dots, but it also shows the sheer magnitude of the two. So when these two overlap perfectly and they're perfectly circular, the fourth dimension is spot on. And we can also see, even though it's hard to see when it's animated, this shows each element of the initial message vector and each element of the final message vector, just to further help you understand how close they are and the differences that the rotation axes make. Once again, I'll unpause the animation just so you can see how hectic this can get. So in terms of our code for 3D and 4D, it's more or less very similar with some slight differences, such as how the arcs between the intermediate message vectors were calculated, which was a lot harder to 4D as we had to work them out based on two rotation axes for each one. For the most part, a lot of the difficulties came in applying the support diagrams around the sides, especially this one down here. And a lot of the work was trial and error, but it was good fun to do. So I hope this video has provided you with a good explanation of the CLUViz components of the project, and I really encourage you to download the software and have a play around with it for yourself. For more information regarding the implementation of either of the visualizations for 3D and 4D, please feel free to read through our code, the wiki, especially for the theoretical proofs shown on the geometric algebra page or the final report, or feel free to contact us, especially if you're going through the code. Really quickly, just with 4D, as you can see, we've got what we think is a sufficient amount of commenting. We go through as the initial setup and settings. We declare the sliders, which are these bits down the bottom. And a lot of the initial stuff's defining all the colors, the shapes, the initial spheres, and the workable space, before we start going into the more theoretical stuff like how to calculate each individual message vector with geometric algebra. Okay, well that pretty much concludes this walkthrough. Thanks for your time.